Good morning, everyone. I should be live now. I think there's a bit of lag, so I think you're going to have about, 20 seconds of me faffing around before you actually see me, but hopefully you can see me now. And yeah, I hope you've all had a good week this week and are ready for the weekend. Let's get right into it. This is a very exciting week, I think. Big news. Big news for big things and big news for little things. But before we get into, here's the title for this week. Before we get into any of this week's stuff, I think it's worth covering some housekeeping things first. Particularly pointing out something from last week's live stream where I noted that the hand part down the bottom was wobbling around a little bit. Some people had some very good suggestions. I'm realizing now I should have taken little screenshots of their comments, but if you go onto the last live stream, you can see them. People were suggesting to clamp the strings against the plastic parts to hold them still, so that way the bottom part couldn't move around. And I've done that. So now this is what it was before. So I could force, like, this is pushing kind of hard, but I could still force quite a bit of movement in there. And then adding in these tiny little clamps. It hasn't fully clamped the string, but it's done a fairly good job. So I'm pretty happy with that. And to be honest, I think it's fair after some of the stuff that you'll see in a couple minutes. It's very, very, very likely that I'm going to be completely remaking this bottom part anyway. So I think this bodes very well for adding in inbuilt clamps into this part. I think if these little black bits were actually like in the part rather than being something that I've just tacked on afterwards, I think they would do a much, much better job. And I think that's a phenomenal idea. I was scratching my head for a while about trying to figure out how to route this string around so that that bottom part didn't move. And this is a very elegant solution. So thank you. I should have screenshotted your comments and given you proper attribution, but you know who you are. Those few of you who said that. So there's another thing that I meant to say or to ask last week, but I forgot to, is how do I send, I plan to put some computational things on the hand, on the platform as it moves around, and I need to send that data from the platform down to the base. So to give an idea of what I mean by this stuff up here is going to have sensors and that sort of thing in it, and I need to get that data down to here. Well, around here where all of the computer, like the main computer is. And I can't think of a super good way to do that, to get this data down along here. One option that I've thought of is to get a cable that goes like along here and then has like a big loop and then down one of the legs. And this loop would accommodate for when that leg expands, the loop can just get pulled tight. I don't really like that though. It seems very inelegant. I'm not a fan. Another one is to have like, I don't know, like a coil. I don't know if this is a thing, but getting like a coil of wire and just having that run around. So if that runs like around here, and that way that can expand and contract as the thing moves around. Maybe, I don't know. If you have any ideas, please let me know, because this is something that will need to be done, sort of soon. I think the coil should work, but whatever. And big news as well, the project now has a proper GitHub page, which is something that I have known for a long time this project will need, but I didn't know anything about GitHub before and was just very confused by the whole thing. I didn't know that GitHub Desktop was a thing. If you don't know much about GitHub, GitHub Desktop is a thing, and it makes everything make a lot more sense. If you don't have that, everything's, for me at least, it was very kind of opaque, but now it's all set up. And the link is here. There's also a link in the description of this live stream if you want to check it out. And big thanks to Joshua Riddle and Finn. I don't know if I want to say your last name the way that I want to say it because I might get demonetized, but thank you, Finn and Joshua. That was, you guys were instrumental in me getting this GitHub page set up, and I think it's a big step forward. A reel or a torsion, I thought of like, there's like the badge rewinders, like the things you have in offices that are like on your hip and you can pull them out and like tap and then like go and it like shoots back. That sort of thing I think would be cool, but I don't know if that works with cables. I don't know. I'm not familiar with ESP now. If you could elaborate, that would be good. Up it, the gazebo simulation. You'll actually see some simulations today, so hang out for that. But all of my simulation that I've been doing so far is just in originally MATLAB, because I had access to that from a uni, but now it's all in Python, and it would be very nice to move to Gazebo. And actually so GitHub was like the big kind of software thing that I was working on like the last 2 weeks, or sort of like the meta thing. And the next meta thing is ROS 2. So same people, Joshua Riddle and Finn, and a couple other people on Zulip are helping me out, giving me suggestions on how to set up ROS. Because I don't know, I think I talked about this like a year ago when I was looking into this, and I just got lost in ROS. There was too many things, and I just didn't really understand how I could best implement it for my project specifically. And I realized that at the time was probably not the right time to be spending so much time looking at that stuff. Now I think it's a lot more useful. Now that there's more people involved in this project, and more people wanting to get involved, I think ROS is a fantastic way to go. Especially as the systems get more complicated, I think ROS will really help with getting everything integrated and getting everything communicating properly. Yeah, that's the short answer. So ROS will be a thing soon, hopefully. Yeah, it will definitely be a thing at some point. Hopefully soon is the point. Yeah. Yeah. So, big news. Let me get rid of me. Oops, wrong one. Jugglebot can throw now, which is very exciting. This is the fastest, or the highest throw that I've gotten Jugglebot to be able to do repeatably. So I've done this like 10 or 15 times, and it's worked every single time. But there are a lot of interesting things to discuss with this. I guess the first thing that you might notice is that the ball does not go perfectly straight up. It hits the side of the hand on its way down. And I'm not super worried about that. I think part of the issue is something that someone mentioned in the last video that I've been aware of for a while and haven't really been too worried about, which is that my homing sequence right now has the actuators going down until they hit this little foam block, and then when they hit the foam block, the current in the motor spikes because it's pushing against something, and then the controller detects that current spike and sets that position as being home, or like a position just off of that. And that's great. It's been super reliable, but I don't expect it to be fully precise because that foam piece is going to squish differently. And I've actually noticed recently, I've been looking at them, and those foam things are like pancakes compared to what they used to be. So I don't expect them to be all doing the exact same thing. So the whole platform is going to be a little bit off. Adding in limit switches would fix this, but that adds in other complications. That will be a bit annoying to do. Another solution for this that I like, the main reason why I'm not too worried about this right now is because I'm actually planning, one of the things that I want to send data down from the hand to the base for is an IMU, an inertial measurement unit that I plan on putting on this bottom part down there. And that will tell me, hopefully very precisely, I've never used an IMU before, so we'll see how it goes, but hopefully that will tell me very precisely the exact orientation of the platform, and if it's a little bit off of like perfectly gravity being down, then it will tilt so that it's perfectly straight up. We'll see, hopefully. So, as I said, this is the fastest that I have been able, well, the highest throw that I have had Jugglebot be able to repeatably do. And you'll notice that it's not super high. Like, it's high. It could probably do 5 balls at that height. I think I can do 5 balls at that height. It's a bit tricky, but it's doable. But this is like full pace, and I don't really want to be running Jugglebot at full pace all the time. So let's have a look at what's actually going on here. We can, the fastest speed that I set the motor to go at is 30 revolutions per second. The drum that the string is wrapping around is 22 millimeters. And so we can calculate a linear actuator speed. So this is the speed that the actuators, each individual actuator is accelerating or moving at, is a bit over 2 meters per second. The hand speed, I will get into why this is the case in just a second, but we have a multiplier of 2. So whatever speed this platform moves at, The hand, which is this little cuff bit that's actually throwing the ball, is going to move at twice that speed. So that part is moving 4 meters per second, which, if you do the math, leads to a throw height of 0.87 meters. And you can see at the end of this GIF, I like put my hand up, and I just wanted to get a very rough idea of how high it was throwing. I have no real way of measuring this. I tried to position the camera so that it was like level, so that when this bit throws, that part is level. But of course, the angle mucks it up anyway to get the actual measurement for the height. So I just put my hand up there and I got a tape measure and measured how high I thought it went, which is about 80 centimeters. So it's very good that my very, very rough guess for how high it went is pretty much spot on for what it should actually have thrown at. But 0.87 meters is not as high as I want Jugglebot to be able to throw at, especially because I don't want Jugglebot to be running at like fairly max capacity for this height of throw. I want it to be cruising at this height of throw. This height of throw is, this is 5-ball territory. We want like 7-ball territory. I'm fairly confident that this hardware can do 7 balls if I change like a bit of stuff around. The main hardware here, I think, can do 7 balls. So how can we throw higher? Well, to answer that, I think it's important to first have a think about how high I actually want Jugglebot to throw. And to figure this out, we can have a look at this nice graph that ChatGPT made for me in like 2 seconds. It was so fast, much faster than I could do it. So just to see what this graph is showing, before we had a throw speed of 4 meters per second and a height of 90 centimeters. And we can see a throw speed of 4.1 is, yeah, pretty much 90. I would like for Jugglebot to be able to throw 1 meter per second, I would like for Jugglebot to be able to throw 1 meter at like half capacity speed. So I guess a max capacity speed would be a 2 meter throw, and 2 meters is pretty good. That's kind of getting on 7-ball territory. So 2 meters is a bit over 6 meters per second. So I want the speed to increase from 4 meters per second to a bit over 6 meters per second. And there's 2 ways. Why can't I erase? All right, we're just gonna have to deal with the red lines. There's 2 ways that I've thought of to do this. One is to increase the speed of the actuators. So as anyone who's following this project for a reasonable amount of time would know, I have done a fair amount of testing on these linear actuators that I've got. And if I'm testing them individually by themselves, the fastest I've gotten them to go is 50 revolutions per second compared to the 30 that I've been getting them at with everything attached, with the platform attached. I don't know fully what's going on here. I'm going to guess it's just to do with the added inertia of the platform. Yeah, I'm not 100% sure, but whatever the case, the fastest I've been getting is 30. I could potentially push it and figure out what's actually happening and get it to go 50, but 50 is super fast, which is a good thing because it leads to a 2.5 meter throw height, but it's also a bad thing because I don't really want to be pushing Jugglebot to its extreme limits often. I want it to be cruising in most of the movements that it's doing. It's kind of annoying that I can't, oh, there you go. Cool. Yeah, so I'm not a huge fan of that option, although it's a possibility. Another option is to increase the hand multiplier. So I said before, the hand currently has a multiplier of 2, which means that when the platform moves, the hand will move relative to the ground at double that speed in general. And so another option that I have for increasing the throw speed is to increase that multiplier. What do I mean by this? Well, this is the current routing of the string, and I should be able to zoom in. This is so strange. There we go. So the string starts, this is like the, oh, I can't draw while I'm zoomed in. All right. This, where the string, can you see my, oh, whatever. The string starts on the hand over here, goes up over the top of the platform, and then comes down, and then attaches down onto the base. And this, I've got a mechanism down here that allows me to like tighten and loosen, well, adjust the length of the string at that point, and that works quite well. But what I'm proposing is having another level of routing, oh, let me get rid of me, so that this string is now a 3-to-1 mechanism. So whatever speed this platform moves up at, this hand will move 3 times that. this will mean that I will be able to hit pretty much exactly that 2 meter throw, and it should work quite well. However, this doesn't come for free. There is another way of viewing what I just said, of every time this platform moves up at 1 speed, the hand will move up at 3 times that speed. Another way of viewing that is that if this platform moves up by 1 millimeter, this hand will move up by 3 millimeters. And effectively what that means is that, why can I only sometimes erase? There we go. What that effectively means is that this length in here will get traversed by the hand very quickly. And so the platform can move up by like 5 centimeters, and this thing will move up in this space by 10 centimeters. So there's basically like an amplification of how far the hand will move. And there's 2 ways that I've thought of to solve this. One is to increase the stroke of the hand, so increase this length in here. But I think there's possible rigidity issues if this was like super long and like all the way down to here, which is where it would have to be. It would have to be 1.5 times as long as it is now. So that would have to be like all the way down there. Possible rigidity issues, maybe. I think the platform as it is right now is quite stiff, and if I basically just copied the same design, it would probably be fine. But there's also the possibility of collisions, and I have found these very hard to visualize when collisions will be an issue and when they won't. The only way that I've been able to reliably figure out if things will collide is by just putting it in CAD and moving things around. And I haven't actually done that yet because a lot of my design here is very parametric, and I think if I change one thing, it's going to really kind of mess things up. But I'm fairly confident that if this hand stroke is much longer, there will be some issues with colliding with the legs, especially in like orientations where it's tilted quite far to the side. So I'm not a huge fan of that. I also would need to buy more carbon fiber tubes, which is expensive, and they take a fair while to arrive, so I don't like that. My second option is to just cop the range of motion loss. So the whole platform will be able to move around a lot less far than it would before, and then also just have a dead zone. And to explain this, we can go to the next slide. So what is a dead zone? Well, this is the ultimate path that the hand will need to follow. So this like gray kind of cup thing is the hand. It's throwing the ball. The green path is its movement when it's in the air, when it's empty. And then the orange path is the path when it is holding the ball. And this here is what we want the hand to be able to actually follow. And to make things simple, I think for now, just think about the hand's movement as the same as the platform's movement. It's not quite, but it's, I think, a good approximation. And this is the workspace of the platform. So these points down here, this is like the base, and this is one of the simulations that I've made up it. And actually, if you're curious, this is, whenever you see this in this presentation today, this is like what folder things are in on GitHub. So have a look in there. They're all in the simulations folder as well. So all of these green dots are basically where they're basically points that the platform can reach. So these purple dots, the 6 of them around the outside, are the nodes of the platform, and the central dot is the center of the platform. And you can just see it here by itself. Like that's the workspace volume. It's really hard to show what this looks like without actually moving it around. So I suggest if you're interested in this, run this code and have a play around with it yourself. And if we just take a slice of this, we can put in that path of the hand from before. And what we can figure out from this is that the lowest point that we want the hand to be moving at is here. Like this is all very crude right now, but it's just to get a very rough idea of what's going on. So the lowest part that we want the hand to be moving at is here. But the lowest part that the hand will actually move to is right down here, right at the bottom. This is like the central bottom point, and that's where it will be resting most of the time. That's where it will go down when it homes to, and that's where, yeah, it's like happy spot will be when it's just sitting there behind me on the floor. Yes, but there's a problem here because we want the string to be, we want the hand to be at its lowest position down here, but we want it to be able to reach down here. because that's where it has to reach to be able to home. And there's a problem here because if it goes down the whole way to home, then the strings will go slack. The strings that attach the whole like hand to the rest of everything else will go slack when the platform is in this zone. And slack strings are bad. I have dealt enough with strings over the last 2 years to know that slack strings are a pain in the ass, and they are to be avoided at all costs. So I really want to make sure that the string will never go slack. Yes. So what I mean by a dead zone is that the hand will be down in its lowest position and the platform can still move around without the hand moving, so the hand is dead, so to speak, without the strings going slack. Is very important. My idea for how to do that, so we only need around 3 to 8 centimeters because we can see here this lowest point is like 590 and this lowest point is like 610. So if we have somewhere between 3 and 8 centimeters of like leeway, then it should be fine. And the strings will not go slack ever, and they will still be able to fit the whole pattern in its workspace. So we only need 3 to 8 centimeters. So my plan for how to do this is in this section up here, have some sort of mechanism that looks a bit like this. So there's I don't know what the word for this is, like a spiral pulley almost. The string will go down. So this string here is like this string here coming down, and there will be a spring that acts in the opposite direction to like wind it back up. This is what will be keeping the tension on this string the whole time. And then there'll be like a stopper somewhere. This is like ground. So that when this thing spins the whole way around, this ledge will hit up against this face, and that will mean that the dead zone has ended, and now the hand is like active. This will need to be tuned fairly carefully. This spring will need to be quite weak, because if this part wants to like pull the string tighter than the hand wants to pull itself back down, it will cause problems, and the hand will move in the dead zone and it will not move as much as I want it to in the rest of the zone. So it all has to be tuned quite carefully, but I think it should work quite well. The main reason why I'm bringing this up now is because I want to know if anyone has any ideas for how to buy or make weak torsional springs. I was very surprised that these things aren't just like a kit. Like you can buy normal springs in a kit and there's like a whole bunch of different sizes and different styles and everything else. But I can't find the same thing for torsional springs, and I want like super weak ones. And the only ones that I can find on Amazon are like packs of like 30 for pegs and for, I can't even remember, a couple other things, but they seem fairly stiff. So I'm not a huge, I don't want to just buy like a bunch of torsional springs that are way too stiff for what I want. And I'm kind of hesitant to make them because I know that I'm not going to be able to make 3 repeatably exactly the same. So yeah, if you have any ideas for weak torsional springs, please let me know. Yes, questions so far? I want to have a look at your comments and have a bit of a drink of water before we go on to the next stuff. Josh, sorry, I didn't see a question before. What's the limiting factor? You have it as a constant acceleration. You will see in a sec. That's what the rest of this is. That's why I want to have a bit of water, because it gets real. Do you think you could get away with a watch main spring? Potentially. That's a good, I hadn't thought about that. Let me write that down. Can you just buy those on Amazon? That does sound along the lines of what I want. I want something super, super weak. All right, let's get into it. How to command Jugglebot. All of this work with throwing the ball has made me realize that my existing plan for controlling Jugglebot might not work too well. And this is a plan that I've had for quite some time. So it's a tumultuous time in my head right now. So what I've been planning on doing so far, I'll first guide you through what I've been planning on doing, and then we'll talk about what my current plans are. But to understand any of this, we have to understand like the root problem itself. The knowns for Jugglebot are the throw position, that is fairly set. The throw velocity, because we know how high we want to throw it, so that is quite set. We also know the next catch position somewhat, and we also know the next catch velocity. The reason why I have these in gray instead of white is because I am starting to think that it's probably going to be a good idea to get this to figure out that position on the fly. So what I've been doing in all my simulations so far, and if you have a look through the simulations directory on GitHub, all of the simulations so far have the throw height and the catch height the same. So it's like throwing from here, catching here. And that is helpful in that it makes a lot of other, like it's an assumption that I have felt I've had to make so far, just because it makes the math actually possible. But I think it will be better. I think the whole robot will be able to perform better if it can figure out the sort of optimum catch position. Because I do this as well. When I'm juggling, I've noticed there are quite a few times when I'll catch low or I'll catch high because it fixes the timing up of the rest of the pattern. And I think Jugglebot being able to do that will make it a much better juggler. So yeah, they're grayed out because I don't know for sure what they will be right now. But I think as far as this part of Jugglebot's brain is concerned, these parts will be known in advance. There'll be like another part of Jugglebot's brain that will be figuring out what these two values are. But this part of Jugglebot that we're concerned about right now will have those as just knowns. So we know where it's throwing from, where it's catching, and how fast those two velocities are. And we need the position of the ball to be smooth. What I mean by this is if we trace out the position of the ball over time throughout its entire path, that has to be smooth. If that's not smooth, something's going wrong. It has to be very continuous the whole way around. And to show you what I mean by this, here is the path of the ball. So this is what I've been doing so far. Path of the ball, we can construct a path of the ball while it's being held. And then to get the hand to go from, so let's say like throws over here and catches over here. Actually, maybe to match it up with the animations later on, we can go throw here and catch here. But to get the hand from here to here, we have to connect those paths up. And so we have this green line that does just that. And you'll notice that all of these curves, if I can zoom in, which I cannot do right now, but whatever. If you zoom in, all of these paths are like they're tangential to each other at that like junction point. And the way that I've been creating these curves is with Bezier curves. So I've been setting this height and this height relative to here. And those are just, I don't know, fairly arbitrary limits, to be honest. And that defines everything that I need for these Bezier curves. Bezier curves are super interesting. And if you are interested in seeing how I've implemented them here, check out this path creator in the trajectory planning folder. So the position of the ball has to be smooth, and we can do that by creating these Bezier curves. But not only the position has to be smooth, but also the velocity has to be smooth. What I mean by like has to as well is this is me telling Jugglebot that's how it has to be. Because I, as a juggler, have had enough experience to know that if the position and the velocity are smooth, juggling is just so much easier. It's so much easier. And so, yeah, that's why I've added these constraints in. And making the velocity smooth looks like this. You have this nice, like the animation's a bit clunky, but it's good. It's clean. It's neat. Look at that. Perfect. So good. And then it comes back down, matches the speed of the ball. Yeah, delicious. Which is great. But it's a lot easier said than done. I have had a lot of time mucking around, so much time, trying to overcome problems like this one, where the hand goes, "Ooh, I don't want to stop, I'm going to go over there, and now I'm going to come back over here, and then now actually I'm going to catch the ball." Don't like that one bit. Why is this a problem, you ask? Well, because the path is known from the last slide. We know how long this path is, and we also know the velocities. So the velocity coming out here and the velocity coming in here. And we also, I didn't write it in the slide because I'm a fool and I forgot, but we also know the time that this path has to take. So we have a lot of restrictions on the way that this can move here. And these restrictions make it kind of difficult to figure out how to travel along this path. Can I add this? No. So To see what the issue is in a bit more detail, this plot here is showing, this is my like first, well maybe not first, this is the approach that worked for the most part, where I set a parabolic velocity. So we know that the velocity is set. This velocity and this velocity, this is like the throw or catch, I can't remember which one's first. This is like the throw velocity and this one's the catch velocity, and these points have to be at that position. And we also know the length of the path. So this like position up here, this is like plotting how long, like what percentage of the path are we along the path right now. So you can see as like the velocity goes down, we traverse the path less quickly. And then as the velocity goes up, we traverse the path more quickly. And down the bottom is just the acceleration, which doesn't really matter too much. Why can't I? The eraser's not working properly. Yeah, so this is good. So my initial approach of setting a parabolic velocity worked fairly well. And the reason why I chose this parabolic velocity is because we need to make sure that between the catch position and the throw position, the amount of distance traveled matches the length of the path. So we know this length of the path, and we want to make sure that we stick to that length of the path because that's the path that we have told the hand that it will follow along. And of course, if anyone is familiar with their calculus, you'll know that position is an integral of velocity. So whatever area this is under here, if the x-axis is time rather than percentage, this area is the length. So this area under here has to be equal to the length of this curve. And I have set everything up so that it is. And that's great, except for when the path is really short or if the speeds are really fast, because that's kind of the same problem, just from two different perspectives. And that's what we see up here. This green path is quite short compared to the velocities involved. And so we end up with this, where the velocity, again, fixed at the top and the bottom. Sorry, at the two ends it's fixed. But because we have, well, I have forced the velocity to be a parabola, it has no choice, because this area under here has to be equal to this length. It has no choice but to dip under 0. And that means that it has a negative velocity, and that's what's causing this kind of like back and forth business at the top. It is a pain. And I cannot tell you how much time I spent trying to figure this out. And what I ended up coming up with is, I don't know, it works, but it's not, okay, I feel like it's fairly good. What I've come up with is to have a nonlinear acceleration. So in the code, if you have a look at this code, which is the trajectory planning code, you will see, why does my eraser stuff up? Basically what's going on is if the velocity is 0 or below 0 at any point, then it swaps, it changes like procedures and changes to this nonlinear acceleration. And what this involves is the velocity will linearly decrease from wherever it is at the start down to 0, because we know that if we do a parabola, it's going to go at least to 0 anyway. So we know that it is probably going to stop. So we just set it to go linearly, and then it will stay linearly at 0 until, I actually can't remember exactly what triggers it to start up again, but it does. Actually, it's the area. So again, the area in here has to be equal to the length of this path, and that sets this acceleration for both of these. And that works fairly well. So that gives us, I think this is the correct animation now. Yeah, it goes down, it stops at the top as you would expect it to, and then it keeps going along. Now, the problem with all of this is that what I've been doing so far involves basically discretizing these paths into like tons and tons of little points. And then I will send, the idea was that I would send all of those points to Jugglebot, and I'd say, move here, move here, move here, move here, move here, move here, move here. And my hope was that that would work. And I haven't actually tried it yet because I haven't had enough time to port this code over to the like actual Jugglebot control stuff. But I'm skeptical that it will work at all, because I expect it to be a bit jumpy at points. So maybe sometimes it will work, and like the commanded point will always be like at least 1 point away, like ahead of what the robot's actually doing. But I would expect that at some times it will be like duh, 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 duh. And I don't want that to happen. I want it to be extremely smooth. And yeah, I'm interested to see what you guys think about this. If you think this point-wise commanding will work, I will be much more inclined to actually give this a go. But as it is right now, I am feeling like my time is better spent to figure out what I'm about to show you instead, because that feels like a much more robust solution. So keep that in the back of your mind, or let me know what you think in the comments. So, yes, see the trajectory planning directory if you want to check out this code in more detail. Yes, would this be suitable? Perhaps not. I think the point-wise commanding will be a bit janky, but we'll see. So my next plan, which I think I mentioned last week, is to send just a few target points. So similar to how, if I go back here, all this work that I've been doing on Bezier curves has made me quite fond of them. And I've been thinking that maybe if I can send just some target points, then maybe that will lead to smoother control. So if, for example, the platform is like here at this dot, I can tell it to go here for, I don't know, like 1/10 of a second. And by that point, it will get to like this point here. But then way before it even gets here, I can tell it, no, hang on now. Actually, I want you to go over here. And then it will start to go in this direction. And then at some point later, I can say, no, hang on now. I actually want you to go over here. And then it will go over here. And then I can say, no, come over here. And then it will, like, I can stitch these points together to get it to move the way that I want it to, is my thinking. And this would lead to no stuttering because it would never get to the point. So it would never be stopping because it's never arrived, which is a bit kind of depressing now that I think about it. And it would also, I could set it up to inherently incorporate the robot dynamics. So I can set the velocity and the acceleration limits for the actual robot, and that will dictate the shape of this curve, which is a lot nicer than this pointwise thing, because this pointwise system that I showed before doesn't inherently do that. And it's very possible that I would be telling the robot to do things that it can't actually do, and it will lead to chaos, probably. Yeah, so this is along the lines of what I've been thinking. And what is going on here is that these colored points, well, I guess the red ones, all of the non-red points are the target points, and it's being told to go to them for 0.17% of the whole time, 0.33 and 0.5. And by stitching these together, I can get the red dot to move in it's very smooth. It's not the same shape as before, but I'm not too wedded to that nice, beautiful curve of the Bezier. It is nice, but it's not critical that, like, between here and here, it doesn't really matter what the hand is doing. It could go like this, it could go like this. Yeah, as long as it's smooth, that's all. As long as it's smooth here and here, that's all that matters. The in between doesn't really matter. So the fact that this is a kind of strange shape, I'm not too opposed to. And to be honest, I haven't had enough time to play around with this to really create a nice smooth shape. This was just fairly quickly. I haven't had a full week this week, so I haven't had enough time to flesh this out fully. And yeah, so one final thing with this is that the color of the line is the color of the target point that it is going to for that segment of the line. And this code is very cool. It's very fun to play around with. However, it has some problems in that it doesn't know anything about the final state. So at the beginning, I tell it what position it's at and what velocity it has. So this is the init pos and init vel. And I also tell it during the simulation, what is your max velocity and what is your acceleration. And then it figures out what it needs to do to move between the points. It doesn't decelerate at all. And we'll see some interesting implications of that in a sec. And it has no awareness of what's at the end. So I kind of mischievously got this GIF to end right as it hits the green dot, but in reality, it just bounces back and forth over the dot. And it doesn't necessarily end at the velocity that I wanted to end at. It just goes straight there. So I would have to modify this idea a little bit so that it takes in both the initial position and initial velocity and the final position and final velocity, and then stitches those together to be smooth. So I don't know. The more I play around with this, the less keen I am on it, but it's still cool. And yeah, if you want to play around with this, it's the Target Approach Sim on GitHub. And so now I've been thinking, what about velocity control? I've heard that velocity control can be good, and it seems pretty legit, but the more I think about it, the more my brain hurts. It's very weird, and yeah, I think it should work, but I need to think about it more. It's been like literally 12 hours since I've thought about this, so yeah, more thought required. But I did think to ask ChatGPT, and its answer has made me more keen on velocity control as an option. This is a pretty convincing answer. Jugglebot does require precise and smooth operation, so there we go. And yeah, as I mentioned, well, I don't know if I did, but I've had a bit of a play around with this simulation because it's kind of fun to mess around with, and you can get some very nice animations and cool patterns emerging. Unfortunately, PowerPoint really kills the speed of these GIFs, so I'm just going to let these roll out. But if anyone has any questions, please let me know, because I am all ears, or any suggestions either, because yeah, I think velocity control is the way, and my idea for that, just very off the cuff, is to take the velocity, maybe I'll put myself back on, you can see the other one as it emerges. Take the velocity profile that I constructed before, so either the parabolic or the straight lines with 0 in the middle, and then tell the motors to go to that velocity, and if they're off of that velocity, then use a PID loop to like bring them back in. But I don't know, velocity control is very hard to think about. It's strange. Yeah, I don't know. And I'm cautious about just doing it straight away on the robot. I really want to make a simulation for it first. So that's probably what I'll be doing. I think that's my main priority right now, is to get the simulation for velocity control done, and that way I can just test that it will work, because I don't really want to break anything. And actually on that note, yeah, look at these nice little flowers that are coming up. It's so good. On that note, I'm very excited by the state that Jugglebot is in right now, because this is the first time, like the other day when I got those throwing GIFs, I think that's the first time that I've done like proper actual testing of Jugglebot, and it hasn't ended in Jugglebot being broken, which is a big step forward. There were a couple points where some magnets came off and like the legs separated, but nothing actually broke. So it's a huge relief that I can actually now do things, test things, run some things, and then just end. It all goes back, and I can leave, and then I can come back the next day, and it's all ready to go again. Huge. I'm a big fan. Yeah, so that is what I've been up to this week. I think next week I'll be doing more control stuff. I will hopefully do some stuff with ROS, because ROS is a big step forward, and I am very excited to move over to ROS. I think that will do a lot for the project, but we'll see how we go for time. I think, yeah, it's a big priority. Velocity control is probably a big one there. Yeah, and thank you, Darkman, for that suggestion. I'll have a look. Every time people suggest like local, whatever, like any store, Australia doesn't have a lot of stores. I don't know. Australia's, I don't know, it's hard to find parts, I think. Maybe I'm just not looking hard enough. Anyway, so that's that. Thank you for joining. I hope you found that interesting, and I hope you all have a wonderful weekend, and I will see you next week.